Okay. Okay. So recording is on, and I can start with blocks. Okay. So blocks are very important. Every processor, um, out there, um, be it a low level, high. Okay. Okay. So recording is on, and I can start with blocks. Okay. So blocks are very important. Every processor, um, out there, um, be it a low level, high level, or even the ones used for, AI, graphical GPUs, they all have a clock. They all need a clock. And the clock decides or determines the speed at which, each line of your code is being implemented at. And so that's why clocks are important. Um, you have different types of digital clocks. Um, just turn on and you're still writing. Okay. And so there are different types of clocks. And one thing to know is that all processors are edge triggered and need a primary input clock, right? So what do I mean by that? What I mean by that is if you go to the previous slide, or what do I mean by that is, if you sort of have a clock signal, um, basically what happens is each line of code gets implemented at this edge or this edge or this edge. So basically, all processors are edge triggered. In other words, things always happen at these clock edges. And these clock edges, well, I don't know if you guys have done digital circuits, but at these edges is where, ones and zeros move out, digital logic circuitry and, in the processor as well. And there are different types of clocks. You have something called crystal oscillators. If you ever open up a motherboard or a circuit board or your phone's board, they look like something like this. And what is it? It is if you remember, those old, well, I would call them old. If you remember those analog wristwatches, have you ever seen quartz written, like quartz movement, like quartz or quartz driven? So crystal oscillator basically is nothing but a quartz crystal, and it's nothing but a naturally occurring material that they cut into very, very precise slices in clean rooms. When you drive and are triggered with an electrical signal, it produces very, very precise clocks, like very precise. And so, applications that need very precise timing, they basically have to have an external clock oscillator, a crystal clock oscillator for providing the clock for its process. So things like GPS. The GPS needs very, very precise clocks. The cellular radio, it time syncs itself with the cellular base station. That needs very precise clocks. So that for those things you always use crystal oscillators. And if you break open one, it's nothing but you have a very fine piece of crystal, and you sort of have the circuitry to drive it. And this produces very, very precise clocks. And so this is one type of clock. You also have built-in RC oscillators that are sort of implemented within the IC itself. And it's nothing but a bank of capacitors and inductors that basically produce the time constant and RC time delay, and they're using this to produce clocks. So the good thing is it's IC based. It's implemented using MOSFET switches, so it makes it more tunable. The bad thing is it tends to be less stable. It tends to be prone to temperature and vibration changes. And so that's why you use it for things where you don't need like very precise timing. So things like the capacitive touch interface on your phone, the infrared sensor, for example, or the light sensor, or like anything where you don't need like really precise control, like any mechatronics, mechanical control stuff. But you don't need to have like really, really fine timing precision. For that, you basically use RC clocks because one, it's internal to the IC, and it's pretty easy to tune. Questions? So, um, you have the option to scale, clocks from either of the sources in the previous slide to a high or a lower clock. And so, for example, this is your clock input. Say it has a frequency FC. So yeah, I guess those of you don't remember frequency. So FC is basically, it governs what this time is. So this time is 1 over FC. And as I mentioned, your processor implements instructions at either this edge or this edge. Our processor basically implements each line of code at every other edge. So it implements it here and then on. So the speed at which your code is getting implemented is basically a function of FC. And then you further have the option of speeding it up using an internal phase lock loop, and in which case the output clock gets a speed of n times FC. And so that is internally done and software as well. And you also have the option of slowing down the clock by basically using a divide by n circuit, which is also internal to a processor. And in that case, your frequency gets slower. In other words, the time between consecutive instructions gets longer, whereas here, the time between consecutive instructions is shorter. Does that make sense? Any questions? So do you see why the clock speed is important for a processor? Basically, because it governs the speed at which your code gets implemented. And all of this, the phase lock loop, the divide by n, it's all internal. It's all controlled by software, and we will see that, how in the next few slides. And so the primary clock in the processor we are using, it can be either an 8 megahertz or a 500 kilohertz or a 31 kilohertz. And you have the option of toggling these clocks depending, depending on your application. And so, you have the option of taking that 8 megahertz clock and, either speeding it up or slowing it down. And same for 531 kilohertz. Right? So these are the clocks available when you're basically using the internal oscilloscope, which we'll be doing for all of our projects in this course. And so why do you need to, throttle your clock? Well, why not just set everything to run at 8 megahertz or the fastest speed, right? Well, the answer is power. The more faster your clock speed, the more power your battery, more power your process consumes. And so if you have things running on batteries, which most of the electronics use nowadays does, you want to be able to throttle the speed just to conserve battery power. And so, for instance, if you're sort of running at a clock speed of 8 megahertz, the CPU and everything on, and say you throttle it down to 31 kilohertz. Well, let's have a look to see what's happening with the power consumption. When you're running at 8 megahertz, the active power consumption is between 3.4 to 4.6 milliamps. And that typically tends to be the case whenever you're sort of in the megahertz range. And it gets even higher and higher when you move into the gigahertz range. But if you slow down the clock, it progressively goes down. And when you're running at 31 kilohertz, the clock speed is a measly 8 to 15 microamps. I mean, it's nothing. It's very little. So milliamps, microamps. So, an order of magnitude of 1,000 in terms of savings of the current being consumed. This is when the CPU is on, everything is on. That's the comparison. But you have the option of leaving the processor in idle modes using software. What that does is it turns off the CPU, but it leaves the other peripherals on, run in the background. So when you sort of use the idle mode, at 8 megahertz speed, the current consumption basically drops to 0.5 to 0.9 nanoamps. So basically 500 microamps to 900 microamps. Right? But if you're running the processor at 31 kilohertz, and you basically are running it in idle modes, then the current consumed is even low. It's like 2 to 4 microamps. It's nothing. And if you're basically using sleep modes and deep sleep modes, in which many of the peripherals also are turned off, except for a few critical ones, then this current consumption goes down to the nanoamperes, like it's even low. So if you're running things on a battery, you have to, move the clock back and forth. For certain applications, for certain speedy applications, you want to run the clock speed at 8 megahertz. But for many applications which are slower, you want to throttle down the clock to lower than 8 megahertz. Questions? So you have the option of configuring external clocks if you're using crystal oscillator. You have the option of connecting it on the primary external I/O pin or the secondary oscillator pins, which are pins 7 to 10. But in our case, we are not using this. We are using the internal RC clock. But just for reference, if you are wanting to use an internal crystal oscillator or an external oscillator, you can apply them here. Oftentimes, you also run processors in either master or slave or sub-slave mode, in which case you may have another processor providing you the clock, to the slave processor. And so if you are sort of running this processor as a slave, you have the option of basically configuring or basically providing clock from the master processor and then putting it here as well. Or you have the option of basically connecting to this processor if you are using this for time-sensitive applications. And then you sort of have, and then you also have the REFO pin. So the REFO pin basically lets you output whatever clock is inside the processor onto pin 18. And so this is useful to have if you want to verify, the clock speed at which you're running at. It's also useful if you're basically using this microcontroller as the master, and if you want to sort of use the clock from the master to produce clocks that basically supply the clocking signal to the state processor. So depending on that, you also have the option of outputting a clock on the REFO pin as well. And that's what those lines of code that I have in the main.c does. It basically outputs the clock on pin number 18, and we just use it for verifying to make sure the clock is switched, the clock is running in the speed you want it to. Questions? Okay. And so how do you configure clocks and what does it look like internally? So as I mentioned, you have the option of applying external primary or secondary clocks on the external I/O pins that I showed you. Basically, I think pins 10, 9, 8, and 7. So that's one of the things. That's one of the ways you can sort of bring in external clock signals, but we're not using that in any of our projects. We're going to be using the internal RC oscillator. And this can be either an 8 megahertz or a 500 kilohertz or a 31 kilohertz, right? And then you sort of also have the option of taking the 8 megahertz and the 5 kilohertz and sort of passing it through a PLL and producing higher clock speed 0. Or you have the option of just taking whatever clock is coming in and just basically sending it over to the CPU side. And which of these clocks gets applied? Well, you have the option of sort of selecting it using this MUX, which is basically just a circuit which lets you select which of these pins to route here on the output side. And then, whatever clock you select, it goes into, you have the option of scaling it down even further. So for example, if you have an 8 megahertz clock and geez, most of your applications are good at running at 1 megahertz, then you can basically divide it by 8 using this post scaler. And, if not, you can just leave it as a 1. And in that case, that clock basically comes out on the CPU. So the CPU is basically the program counter that's running from one line of your code to the next. And that's what decides how fast your code is running. And then, you have the option of basically taking that clock, giving it to the CPU. You also have the option of basically using that clock into peripherals. And you also have the option of outputting that clock and give it to slave processors, right? So slave MCUs. So questions? We talked about that. Yeah, we talked about that. Yeah. And the output, you can output the clock on the REFO pin, which is pin number 18 or RB15 in the digital I/O. So how do you change clocks? Well, the way you do that is by basically just writing into 3 sets of bits in this register called OSCON. It stands for Oscillator Configuration Register. And the good thing is, every family of processors uses the same naming convention. So, if you're programming this particular microcontroller made by Microchip, every other microchip microprocessor or controller uses the same OSCON register name. So if you know how to program one, you kind of know how to program the rest of them as well, right? And so the COSC bits here, basically, it contains the bits that denote what the current clock speed is, right? And so, we saw that we basically setting the preprocessor directives, those hash primer commands in main to run at 8 megahertz. And so when the processor is on, if you look at the COSC bit, so if you probe it, it'll either have a value of 000, denoting that it's running at 8 megahertz, or it'll have a value of 1111, denoting that's running at 8 megahertz as well. If this value happens to be 110, it means you're running at 500 kilohertz. And if this value happens to be 101, it means you're running at 31 kilohertz. So if you want to switch these clocks to a new clock speed, then in that case, you basically sort of write values to the NOC bits, which are basically right here. And so say you want to switch it to 500 kilohertz clock, you basically write 110 into the NOC register or NOC bits. If you want to switch it to a 31 kilohertz clock, you write a 101 to it. And so this is 31K. And if you want to switch it to an 8 megahertz, you have the option of writing a 0002, and that'll basically configure it to 8. So these are the bits that tell the processor what the new clock speed is going to be. Now, to initiate the clock switching or the changing of the clock speed, you have to write to a 1 to this OSWIN bit. And when you write a 1 there, it basically initiates the oscillator switch, the clock source specified by NOSC, which is these here. And basically, once the clock switching is done, automatically the processor will clear this OSWIN bit and set it to 0. Do keep in mind that it takes a few instructions to implement the clock switching. It's not a instantaneous thing. That does produce delays in the code. But yeah, you should be doing clock switching depending on the application to throttle the speed to save on battery power. Questions? Okay. And then you also have the option of, as I mentioned, going back here, you have the option of also sort of scaling down the input 8 500 kilohertz clocks further, right? And if you want to scale it down further, so for example, say you have an application that's running at 1 megahertz, you have the option of basically sort of taking that 8 megahertz and dividing it by, say, 8, or you have the option of dividing it by 101. And that'll basically take the 8 megahertz clock and generate sort of speeds which are, a fraction of that. And so that's done by basically writing values between 0 and writing values between 0 and 7 in the RC bits. Similarly, if your speed is, if your processor is running at a 500 kilohertz, if you write a 000 here, it means it's just uses 500 kilohertz. But you have the option of scaling it down as well to 250, 125, basically divide by 4, 8, 16, 32, 24, 26. By basically writing the corresponding value to the RC bit. So this is just used to scale down the clock even further, if need be. And then lastly, you sort of have a register called the OS-tune. The name suggests it lets you tune the clock. And so, as I mentioned, when you're using an RC oscillator as the clock, as what we are going to be doing, your clock can skew a bit depending on changes in temperature and pressure. And so, if you want to nudge it back to the exact 8 megahertz or 500 kilohertz, you can do that by basically sort of writing values into this TUN bits. And all it's doing is basically turning on or off MOSFET switches, which is basically affecting the R and the C of the RC oscillator, which changes the frequency. It's useful for sort of bringing back or tuning back the clock to an exact clock value in case it's sort of running a bit adrift. And normally it does, like, it'll be normally you want to run at 8 megahertz, but in the winter or in the summer, who knows? It might go to like 8.1 megahertz or 8.08 or 8.05 megahertz. And so if you want to nudge it back to 8 megahertz, you can do that by basically just writing different values to the TUN bits. Questions? And so the function for changing clocks is something that I'm also going to be giving it to you. It's one of the few times that I'm going to be giving you code. And so I'm going to be sharing with you later on D2L a function called new clock. And it basically takes in a variable called clock val. And if this clock val is 8, it'll switch the clock to 8 megahertz. If the clock val is 500, if you send it to 500, it'll switch the clock to 500 kilohertz. If you send it at 32, it's going to switch the clock to 32 or 31 kilohertz, somewhere thereabouts. And all it is basically just basically sort of checking using a bunch of if-else sort of conditions to check what's the value, and accordingly, it's sort of writing these values into another sort of user variable called COSC and OSC. And basically, these lines of code here, this is where I'm scaling it further. If I want to scale the clock even more, these lines of code basically are doing a special write into that OSCON register that I showed in the previous slide. And then after that, I'm basically sort of setting the OS when bit equals to 1. And that's what basically initiates the clock switching. And till the clock switching is done, it stays here in this while loop. Once it's done, it comes out. But I'm also doing something else. These things, these SR bits, these commands, we will look into these when we get into interrupts a bit more in detail starting next week. But for now, just know that all it's doing is it's basically turning off interrupts. And then once the clock switching is done, it's enabling interrupts. And the reason you want to do that is because clock switching is a very sensitive operation. And so, yeah, you want to enable or you want to disable any events or interrupts to affect the processor while the clock switching is happening. So during that time while the clock switching is happening, I'm disabling the interrupts by basically these two lines then. And once again, we'll go into it a bit more in detail when we talk about interrupts. Questions? So this function will switch the clocks for you between 500 kilohertz, 32 kilohertz, and 8 megahertz. So do use this function often to scale up or down your clock, depending on your application. Right? And so in your driver projects, for example, if you're doing something which is human controlled or mechanically controlled, which is slower speed, if you're using 8 megahertz for that, then you will lose points, right? Because you're basically draining power. You want to be running at 500 or 31 kilohertz. Right? Similarly, if you're doing communication at high speeds, you want to be doing things at 8 megahertz. Yeah, we are looking at how you throttle the clock and conserving power in your coding application. So I think a lot of embedded coding is often known as energy-aware embedded coding, just because of the constant need to throttle clocks to save battery power. And that's what's happening in your phone as well. Like your clock is never steady. While your phone's in your pocket while you're listening to this lecture, hopefully, you're running it at a very slow clock speed. But the minute you lift it, turn the screen on, the clock ramps up. So even behind the scenes, there's a lot of clock switching going on all the time. Questions? So, let me actually before I get it. Yeah. So normally, just want to say that the speed at which each line of the assembly code that gets generated from your C code gets implemented at is basically given by the time duration between this edge and not the one after, but the one after. That's duration is what governs your code operating speed. Right? And so the formula for that is 1 over f clock times 2. And so this value could be, if you're running it at 8 megahertz, this value could be F25, excuse my handwriting, at 8 megahertz. If you're sort of running it at 500 kilohertz, it's going to be, some microseconds as well. If you're running at, 31 kilohertz, I believe it's tens or hundreds of microseconds. And this is at 31K speed. So yeah, clock speed affects the speed at which your code is running. And so I think the next sort of driver project, we haven't posted it yet, but you can start practicing it right now. We want you to modify driver project 2. So in that, if you remember, you're using while for loops. You have to implement the LD blinking at half a second, 1 second, and then 3 seconds. Try doing that, when your clock is running at 8 megahertz, which it already is by default. Try doing it also at 500 kilohertz and 31 kilohertz. And you will have to adjust the counter value depending on the clock speed that you're running at. So a good exercise to get started. I think driver project 3, and onwards might be based on clock switching. So it's a good idea to get a hang of. So any questions? So if you come back to code that I've shared with you, can you see the screen now? The screen showing the code? Yes or no would be helpful. The chat window. Okay, good. So these lines of code is basically enabling that clock on pin number 18, right? The REFO pin. And all I'm doing is I'm configuring that pin as an output. And I'm basically turning on the clock on that REFO pin and doing things there to basically show up on pin number 18. So that's basically this line of code. So if you're running this code and if you probe the pin number 18 in an oscilloscope, you will see the clock speed. It'll either be, you see the clock signal, it'll either be at 8 megahertz or 500 kilohertz or 31 kilohertz, depending on how you switch the clocks. Okay, questions? Okay, let me get started with intros.